Hello, my name is Darko Bozinowski, and I'm presenting a paper titled A Modeling Tool for Reconfigurable Skills in ROS. This work is based on a research collaboration between TU Delft, University Polytechnical de Madrid, and the IT University of Copenhagen. The paper has been co-authored by Esther Aguado, Carlos Hernandez, Mario Garzon, Ricardo Sanz, and Andrei Vasovsky. Today's talk will include details about the scope of our research, which is conducted in a collaboration between software engineers and roboticists and is focused on adapting robot control architecture. I will discuss the Metacontrol for ROS2 systems, that is a framework that captures the design and runtime elements to specify and realize adaptable robot control architecture. Finally, I will place my attention to the main contribution of the paper, that is the ROS design tooling, that allows system architects to specify the robot architecture through a set of skills. I will conclude with a demonstration of the approach in a patrolling mission. New robotic systems need to operate in dynamic environments under uncertainties that influence the outcome and the quality of the mission execution. They need to cope with uncertainties and be able to employ different strategies for different contingencies and system errors that can happen during the mission execution. In this context, there is a pressing demand for solutions that integrate self-adaptation in robot control architectures. The existing work on self-adaptation require major redesign of the robot control architecture, and most of these approaches use tools that are unfamiliar to the robotics community or are hard to reuse across application. We present the ROS approach. ROS is a model-based solution that integrates self-adaptation in robot control architectures. It has been developed as part of the Robosis ecosystem, which favors model-driven engineering as the main technology to realize and deploy robotics applications. The Robosis approach specifies different levels of abstractions. In our project, we focus on the skill level. The ROS framework, uses ontologies to represent and reason with runtime architectural models, which promotes reusability, but also considers explicit separation of concerns between mission-specific logic and system management. Here, the ROS framework is focused on the system level. At the runtime phase, the main component at the runtime phase is the metacontroller. The metacontroller is the component that drives system adaptation at runtime based on the design time architectural model. It performs architecture analysis and adaptation decisions using a domain-specific knowledge in the form of SWIR rules. Our design tooling consists of the ROS language, ROS transformations that generate artifacts that can be directly deployed to a robot, and a library of skill definitions for navigation. The library of skill definitions for navigation is conformed to the ROS language and consistent with the ontologies in the Metacontrol framework. To extend the usage of skills beyond the navigation domain, other libraries need to be developed. Initially, a domain expert develops a set of conceptual rules for a domain, which then can be encoded in an ontological form. The tool we developed aims to help ROS users to create architectural variants in the form of robot skills. So here, the system architect creates the architectural model in the form of skill variants, and afterwards, using model-to-model transformations, two artifacts are generated. One artifact that is deployed at the system modes level, and the other one that is used by the metacontroller to reason upon. The ROS language is based on the ROS meta model, which is strongly aligned with the Robosis meta model. In this context, for a task to be executed, the robot needs to possess a certain set of skills. The language follows the conceptual decomposition of skills in the decomposition Robosis meta model, which separates the specification of the skills definitions with their corresponding skill realizations. In this direction, the ROS language has two main elements: constructs to specify predefined skill definitions that are generic and platform independent, and skill realizations that are platform specific elements. A skill definition is characterized by an input, output, that these attributes that depict the skill data flow, and a result, which models the possible progress of a skill that can have at runtime. Every skill definition is also associated with a quality attributes that are relevant for that skill. It is important to note that MROS allows architects to model various skill realizations for each skills. In this context, the system developer needs to provide ROS2 implementation of the skill realization. We define skill realization through the following main concepts. The first one is the system architectural variant that is expressed in the form of system mode. Then we have the quality attribute model, a concept that provides information about the expected quality of a realization. And the third one is the context, a concept that provides information about the settings in which the skill is realized. A system model is a concept that refers to a system configuration that can be deployed at runtime. It is a pre-existing concept that comes from the integration of the system modes library in the Metacontrol framework. Here we can see an example of a system that is described using the MROS language. On the left side, we can see one skill definition to navigate that is characterized by three quality attributes: safety, performance, and energy. And it has one input, which is the distance to the wall. This skill definition corresponds to a skill realization of a slow mode, which has 5 components, and each of the quality attributes defined in the skill definition have obtained specific values. And then in the end, we define the context of the skill realization. In this example, the context is the default context. We generate two types of artifacts. One is the application-specific individuals in the knowledge base in the form of ontology. The ontological structure that we generate consists of the following elements: components, which are information of which running components influence the availability of skill realizations; function designs, which is conceptually equivalent to the definition of a skill realization. It is a concept that has been done as part of the Metacontrol process, but in general, this is equivalent to the skill realizations that we've been discussing earlier, and it contains information about the skill that is realizing and the expected quality. The expected quality, which is a concrete value of a quality attribute for a specific function design. The system modes is a runtime model specified in YAML format and consists of the following elements: system structure, which contains the components or the parts that comprise the system; system modes, which defines the modes on the system level, and each system mode is defined through a set of components and their corresponding component modes. Component modes is the definition of modes of the individual components. Component modes are defined through an assignment of the different values to their corresponding component parameters. Finally, we realize this Metacontrol approach in a patrolling mission where a Tiago robot needs to navigate in 5 different locations. We used one skill definition, which is to navigate, and we realized 6 different skill realizations that differ in terms of the expected quality for 3 quality attributes: the safety, the performance, and energy efficiency. We introduced system contingency during the mission execution, which was the laser failure and the low battery. And during the mission execution, using the Metacontrol approach, the robot was able to reconfigure and choose a different alternative for system adaptation. The Metacontrol observed the contingency type and allowed the robot to select a new configuration which was suitable for the current context. We presented a modeling tool for reliable robot skills. We introduced MROS model-to-model transformations, which translate this high-level mission system specification into 2 artifacts: artifact for high-level reasoning in a form of ontology, and artifact for deployment in a form of system configuration. We demonstrate the concept in a patrolling mission. As our future work, we will extend the number of demonstration scenarios and create new skill libraries for perception manipulation, analyze the language completeness, and then in the end, we'll investigate the usefulness of the tool for system architects. Thank you for your attention. Looking forward to meet you at ROS 2021.